So now let's talk about rate law. Rate law. There's a couple of things I want to cover with this rate law. So rate law is basically describing how concentrations are changing in our reactions. That's what a rate law is. It's telling us how, or describing at least, our concentrations changing over time. Now, the rate of our reaction is proportional to the concentration of each reactant. Okay, and this is depending on what's it raised to. So what does all that math lingo means? It means this equation right here. So this is our rate law, everybody. Rate equals K, as I mentioned it earlier before. So rate equals K times the concentration of A raised to a power. So in this case, we know what a rate is. That's concentration over time. But what is K? K is what we're going to refer to as our rate constant. Our rate constant. All right, so this will always be a constant depending on the reaction. So what we want to understand with rate constants is that every reaction has its own rate constant, right? So it's dependent on the reaction. Now, N is what we call orders, whatever is raised to, whatever our concentration is raised to. And we're only going to talk about three orders today. All right, we only have three types here that we'll mention today. There are others, but we're only going to mention the common ones. Okay. So the exponent of each reactant in the rate law is called an order. As I mentioned before, this is your order, your N. And your order is always going to be in respect to reactant. So basically, you're only going to see your orders be associated with reactants. You're not going to see an order for a product. Remember, because that's what we're forming. All right, so you're not going to see that happen there. So the sum of your exponents on reactants is called our order reaction. Okay. Now let's talk about the three main orders. We have 0, 1, and 2. 0, 1, and 2. We're only going to get 0, 1, or 2 for our N here. That's it. So we're going to go over 0, 1, and 2 in a bit. But just understand, right, with your rate law, you're only going to have these three different orders. Okay, these three different orders. Okay, and they all mean they are their own thing. A zero order means a certain thing, a first order means a certain thing, second order means a certain thing. And they're all impacting your reactants, which are making your products. So for instance, if we had a rate law, say for instance, this is our rate law. Rate equals K times concentration of NO2, then concentration of O2. So this, if I'm just looking at this rate law, this is telling me that my reactant, which is my NO here, is second order, right? Because this N is telling me the order of my reactant. That's how we're looking at these. All right, so this is second order in respect to NO. And then my O2 is 1. Now we know it's 1 because we don't see a number here. All right, so either you're going to see a 2 or a 0. All right, whenever we're trying to do these orders. Okay, so in this case, because I don't have a number here, this is the first order. And my order of our reaction is adding up our exponents. So 2 plus 1 means that we have a third order overall. We're going to talk about two types of rate laws here. Differential rate law and integrated rate law. So differential rate law is basically telling us how our rate changes with concentration. Okay, so what we've been seeing here. All right. This is basically what we've been doing. Differential rate laws here. Okay, with our, notice it looks very similar to the other rate laws and different equations we've been using. Our concentration over time. So this is once again telling us how our rate changes with concentration. Now, integrated rate law is a bit different as it's telling us how our concentration depends on time. So once again, differential is telling us how our rate changes with the concentration. So your concentration is impacting your change here. integrated rate laws is telling us how our concentration is, in this case, being dependent on time. Okay, so integrated rate laws are really useful for a couple different things. In this case, they're going to help us determine if a reaction is fast enough to be useful. All right, so usually people are using integrated rate laws, or they're going to help us figure out the exact steps for a reaction. Our concentration over time. We got our time as the excess, concentration here. And what we're going to see, right, is that, as I mentioned, we have three types of orders. We got zero, first, and second order here. All right, so zero order, we can see our n is equal to 0, first order n is equal to 1, second order n is equal to 2. All right, so when we're talking about our concentration related to time, right, we can see how our 0 looks, our first order looks, and our second order looks. Okay, so we can see here, right, with 0, over time, it's kind of like a linear progression going straight down. And then we can see that, right, first order going straight down, second order, we can see that this is actually the fastest decreasing over time. What I'm going to show you over here is how our rate is going to be impacted by these orders. So this is our rate, right, versus our reactant concentration. So basically, what's happening to our rate when we have a 0, a first, or second order? Okay, so if you have a 0 order, right, which we mentioned over here, our concentration, this linear progression going down, right, the same thing, the same rate over time, it has this type of feel to it, right? So basically, our 0 order, it's going to be constant, right? So over time, everything is constant. And that's what we see here, right? Everything's constant. So that's the reason why once it starts at that rate, it's just going to keep going down, 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 down till it's done. Let's look at first order, which we saw over here, right? First order. So how does that relate when it comes to our rate and concentration? So as we increase our concentration over time, we're going to see our rate will be in this linear progression over time, which we see over here, right? It's going, if we went further, it will keep at the same rate, the same decrease. And then let's talk about second order, right? So second order, we notice it's going to decrease the fastest. It was decreasing faster. So how does that impact our rate versus our concentration? For second orders, this is like the fastest one. Just think of it as the fastest one, right? To where we have our concentration and our rate. And we're going to see, right, starts off slow, but then it just goes. It just goes super fast to where eventually, and if we know how graphs work, so this is a linear progression. This is happening at a much faster rate with the curve here exponentially. Ooh, I killed that word. Yeah, this is happening at a much faster rate, right? So it's just going super fast, going straight up there, quick. All right, so basically 0 order is constant, first order is linear, second order is the fastest of them all.